Alrighty, howdy folks. Chapter 14, Section 6, Chapter 14, Section 6, Directional Derivatives and the Gradient Vectors. Fascinating one. Especially this gradient vectors and all that. My goodness. I'll talk about it. You'll see why I'm making such a big deal about it, why I'm so excited about this. One thing was when we talked about regular partial derivatives, that is partial f with respect to x and partial f with respect to y, what we did there was we looked at what happens to f if we were to hold y constant but change x, move a little to the right of the original point is x sub 0, y sub 0. Excuse me. Move just a little bit in the x direction by an amount h. It could be positive h or negative h, right? And then look at what the difference quotient is. That means, given a function f of x, y, at a particular point x sub 0, y sub 0, it would have a certain z value, right? F of x sub 0, y sub 0. So if we move a little delta x, h is the same as delta x, a little from that point, you are at a different point now, whose coordinates are x sub 0 plus h and y sub 0. What's the value, the z value at that point? And you look at what the change is in the z value and divide that by h, and you try to look at what the limit of that would be as h approaches 0. You never make h equal to 0. So that's the original derivative concept, right? So here we move along x direction. In the partial f with respect to y, we hold x constant and move along y direction. Okay, all that is fine. But the question then becomes, what happens if we were to move not in the specifically x or y direction, but some other arbitrary direction? How much would the function change? You see the beauty of this one? Along x and along y. Yeah, we are familiar with that. But what if we are talking about some arbitrary direction? Well, the moment you talk about a direction, you can use the concept of vector, especially a unit vector. Because why do we say unit vector? Because the magnitude would be 1, and it's more the direction that we are interested in. And so we find what is called a directional derivative of f in the direction of a unit vector u, whose components are a and b. Is this beginning to make sense? Not x or not y direction, but some direction u, but the unit vector given by the unit vector. What would that be? Well, it turns out you call that as uppercase D sub u to indicate, hey, I'm taking a directional derivative in the direction of u of this function f at that point x sub 0, y sub 0. What is that given by? Well, that is also a different quotient, just as limit as h approaches 0 with a denominator h. But here is where the change happens. You look at what the function's value is at x sub 0 plus h times a plus y sub 0 comma y sub 0 plus h times b, where a and b are the components of the unit vector u. Cool? That's the definition of a directional derivative. Now, immediately let's look at a theorem. If f is a differentiable function of xy, then f has a directional derivative in the direction of any unit vector u, ab. You're guaranteed. Anytime a theorem guarantees something, that's a very powerful theorem. Okay, if a function is differentiable function, then automatically you're guaranteed the how should I put it? Okay, let's say the differentiability of the function has been established based on our partial derivatives f sub x and f sub y. So you have established the differentiability. Then guess what? You can be guaranteed that the directional derivative in any direction will automatically exist. That's the key. Okay, and it's simply given by, how do you find this directional derivative, right? Check this out. All you do is, you know the partial derivatives f sub x and f sub z. Oh, come on, Sammy. Sorry about that. F sub x and f sub y. So we know them, form a vector out of it, and take the dot product with this unit vector u. That's it. You know how to find partial f with respect to x and partial f with respect to y. Well, form a vector out of it and take the dot product with u. And then there is a special operator that we use, just like the partial derivative was a special operator, partial symbol. There is another thing called del, or gradient it is called. If f is a function of two variables x, y, then the gradient of f, or people call it as del f, is the vector function del f. Look at that. It's like a inverted delta, and it is a vector del f. And that is defined by del f of xy is just partial f with respect to x I, partial f with respect to y j, plus partial f with respect to y j. In fact, I don't know why I didn't write that. Del itself would be partial with respect to x I plus partial with respect to y j, and you typically would say del of some f, like we have here del of f, which would be partial with respect to x I plus partial with respect to y of j of f, or it can be written this way. Okay, next. So what's the difference between that directional derivative and this? Nothing. So nothing in the sense du is nothing but the del f dotted with u. Cool. So let's go back. So originally we saw that du of f of xy, the directional derivative along the u direction, was this dotted with u, right? And we are saying this part is the del part, del f. So we have du to be del f dotted with u. Cool. All right. From the above, this statement, that is, when I first looked at it, it was not so obvious. So I had to think about it. Let me clarify this. From the above equation, it is clear that the maximum value of the directional derivative occurs when the direction of u is such that du equals del f. Is that what Americans call clear as mud? What? The maximum value of the directional derivative. So this guy has a maximum value and a minimum value, something like that? Why would that be? Well, that is because we are taking a dot product with u. Right? So as u changes, would you agree that the dot product starts to change? Del f is fixed. The moment you know the particular function f, you figure out f sub x at that point and f sub y at that point. There should be a y. I'll fix it. F sub y at that point, that part is fixed. But then when you start taking a dot product with vectors in different directions, that dot product is going to change. So along one particular direction, this would have a maximum value. And when these two vectors are, maybe I should, let me put that in the form of a question. Think about it. When would this dot product actually be equal to 0? Will it ever be 0? Yeah, the dot product of two vectors is 0 when the two vectors are perpendicular to each other, right? Orthogonal to each other. So that would happen, that this dot product would be 0. Now, here I have an illustration of this. Let's say u is a unit vector and we take some vector a. It could very well be this del f vector, the gradient f. If we have this one and we want to talk about the dot product of a dotted u, what exactly is that? You remember back we learned about projection, scalar projection? That's what we are talking about. Because this vector u happens to be a unit vector, a dotted with u is magnitude of a times magnitude of u, which is 1. So magnitude of a times 1 times cosine of the angle between these two vectors, right? Cosine theta. If that theta changes, cosine theta changes and the dot product changes. In other words, this is nothing but the projection of a onto u. That is what a dot u is. That vector. I shouldn't have made it into a vector. It's not a vector, it's a dot product. So it's just the magnitude, the length of this black arrow. Okay. And when would this be maximum? At this time, would you agree a dot u is actually smaller than a? Yeah, because that's like the hypotenuse. Hypotenuse has got to be the biggest side. However, if the direction of a coincides with the direction of u, wouldn't that be a maximum value? In other words, theta is equal to 0. So a dot u would simply be equal to the magnitude of a. And that's the maximum value. Okay. Now, man, what's that got to do with all of this stuff? So that is a crucial practical point. So this is the point I'm making. The maximum value of this directional derivative would be in the direction of del f. Del f is a vector, which means it has magnitude and it's and a direction. In that direction, this directional derivative has a maximum value. And that comes into play in many, many, many practical things. So keep that in mind, right? Next, let's solve some simple problems. Find the directional derivative of f of xy equals this at the point 1, 2 in the direction indicated by angle theta. Well, we need to find the directional derivative, that is du, and we know we need to find a partial derivative, make a vector out of it, and take the dot product with u, right? Del f of xy dotted with u. Can we find f sub x? Yeah, that's easy. F sub y would also be easy. And this should be, I should change it. F sub y would be easy. How about this u though? U, we have been given that the angle theta equals pi thirds. That's the direction. So we make use of that angle theta equals pi thirds with respect to the positive x-axis and figure out what u ought to be. Here, because the direction is given by angle theta, the unit vector is nothing but cosine of pi thirds, sine of pi thirds. Cool? And cosine of pi thirds, cosine 60 degrees is 1/2, sine 60 degrees is square root of 3/2. That's what I did. And the rest is straightforward. Find f sub x and f sub y, plug those and evaluate them at 1, 2. X equals 1, y equals 2. That's what I plugged in. And we got the del f vector to be 6, 12. Take the dot product with the 1/2 square root of 3/2. That's it. That's the directional derivative. That's the amount of change this would experience, this function would experience if you were to traverse along the direction of pi third, an angle of pi thirds. That's what it says. Next, similar problem, theta equals negative pi 6. Maybe I did this because I just wanted to show you that the maybe slightly more complicated derivative. Slightly. That was the whole idea. Same idea, f sub x, f sub y, find del f. We found u already. Take the dot product and we get dot product is a scalar, so we just get a number. Cool. Now, find the gradient of f. Now we are talking about gradient of f. That is the del f. Evaluate the gradient at p at this point, and also find the rate of change of f at p in the direction of the vector u given. So they have given us a direction. Notice now this is a function of x, y, and z. Don't let that cause panic to you. We can easily extend the 2 dimensions to 3 dimensions. Okay, so find f sub x and partial with respect to x, hold y and z as constant, so this becomes 2xyz, yz cube, right? And evaluate that at that point p, 2, -1, 1 by plugging in, and we get -3. Similarly, f sub y, partial f with respect to y, hold x and z constant, so the first one should be x square z, and the second term should be xz cube. That's what we have, right? Minus xz cube. Evaluate that. Similarly, partial f with respect to z. And so del f in this case is simply f sub x comma f sub y comma f sub z. That's the beauty of this. See, the operator del, we just need to say del f. And depending on the circumstances, we will say, oh, you mean f sub x comma f sub y comma f sub z? Yeah, if you have a 3-dimensional system, that's what it would be. So because of that simplicity, we use the operator del. And del f evaluated that 2, -1, 1. Well, we figured out each of these values, right? -3, 2, and 2. So that would be that vector. So what have we done so far? We have figured out the gradient of f. Yep. And evaluate the gradient at p. That's precisely what we have done here, b. And now find the rate of change of f at p in the direction. That's nothing but du. And so we take the dot product of this vector with u. And we get 2/5. Cool. Simple, straightforward. All right. Moving along. A similar problem. Yeah. Find f sub x, f sub y, f sub z. Evaluate each of those things. Del f. And vector v is 1, 1, 1. So, this, yeah. Right. One difference here though. Whenever people say find the direction, find this directional derivative in a certain direction, make sure that the direction that they say is actually a unit vector. In the previous case, it was. But when you look at this v is not a unit vector. Why not? Because what's the magnitude of this? Square root of 1 square plus 1 square plus 1 square. That is square root of 3 is the magnitude of this. So that means it's not a unit vector. So we need to find the u, the unit vector, by dividing the vector v by its magnitude. Now 1 over square root of 3, 1 over square root of 3, that is the unit vector. Cool. Make that small, be careful about that little aspect of it, and you should be fine. The rest should be fairly straightforward. Cool. Yeah, that's the reason I did this problem. What else? Find the maximum rate of change of f at a given point and the direction in which it occurs. That's an interesting one. What's the maximum rate of change of f? Well, that's just the del. Right? Maximum rate of change of is nothing but the magnitude of del f. And it occurs in the direction of the del vector, the gradient vector. Okay, so let's figure out f sub x, f sub y, and f sub z. And so del f evaluated at that point 1, 2, 1.5, 1/2, 1, 2, 1, 2, and 1/2 is 0. The x component, y component is 1/2, and z component is 2. And so the maximum value would be the magnitude of that. You know how to find the magnitude of a vector, and the square root of the sums of the squares of the components. That's what I did. And so far as direction is concerned, it is in the direction of this vector del. That means in the direction of 0, 1/2, 2. The only thing that you need to make sure is you better give the unit vector. This is not a unit vector, right? Is it? 1/4 plus 4. No, it's not. I should have figured out the unit vector. Maybe I can get away without finding the unit vector. Just mentioning this would be fine. Yeah. Cool. This is what I really wanted to get to. What's the big deal about this gradient vector? Check this out. The gradient vector, its direction tells you the direction in which the function is changing the greatest. Do you agree with that? Let me repeat that. The gradient vector's direction tells you the direction in which the function is changing the most. Now, that little principle alone is very essential in practical life. For example, you take water. In which direction does water flow? From top to bottom, from a higher level to a lower level, right? Well, what else? The water looks for the direction in which the slope is changing the fastest. The height is changing the fastest. In which direction is it changing? And that is the direction in which water flows. Now, that is precisely what the gradient vector indicates. As you can see in this map of a hill, let's assume that this is some kind of a hill. Now, notice, what are all these curves? These are the level curves, right? What does it mean? What do I mean by a level curve? That means every one of these points is at the same height. Would you agree? That's what a level curve is. Now, these points are at a slightly different height, but from the previous one, but they happen to be all this point and all these points are at the same height. They are at one level. Now, what does it mean if we were to traverse along a level curve? That means our height is not changing at all. Would you agree? In this context, as we traverse along a certain level curve, the height is not changing at all. So now if I were to ask, well, if along the level curve the change in height is 0, in which direction will it be maximum? The answer is perpendicular to it. If in one direction it is 0, perpendicular to it should be the maximum. And in fact, the gradient curve is nothing but normal to the level curve at that point. If we can draw a normal here, that means a tangent and then perpendicular to it, that is the direction in which the gradient vector would be pointing. And so you can figure out precisely how water will flow. Let's say I put a bucket of water at that point. Which way will it flow? Will it flow up? Nope, definitely not. Will it flow along the level curve? Nope, it's not. It comes down. It looks for where you have this greatest amount of change, or steepest descent, it is called. And that is actually perpendicular to the level curve at this point. So this point is somewhere over here, let's say. So we draw a tangent and then a normal, and water flows along that normal. So that means it descends vertically down, sort of like that. And then it reaches this point. There again, you have to look at the normal to the curve, and that's the direction in which flows. It keeps on flowing like that, wherever you have the steepest descent, determined by the gradient vector. That's the beauty of it. Now, not just water flow, right? Even temperature, heat transfer. Heat flows from a body at a higher temperature to a lower temperature. So once again, you are looking at what are called isothermals, things at the same temperature, and heat starts to flow from one isothermal to the lower isothermal, from 90 degrees to 80 degrees, to 80 degrees to 70, and so on, in a similar way. And that little insight is what actually causes us to, as engineers and physicists, learn more and more about these gradient vectors. Cool? That's it, folks.